Here's solutions for some homework problems from Chapter 6. It's toward the end of the chapter now. You're thinking big picture, trying to put it all together. So 61, let's see what we got. We've got a block of mass m, 4 kilograms. It's on top of another block of mass 5 kilograms, 4 kilograms, 5 kilograms. And we got a force acting this way. To cause the top block to slip, to cause the top block to slip on the bottom block, on the bottom one, while the bottom is held fixed, a horizontal force of at least 12 newtons must be applied to the top block. Okay, so what they're saying there is if you hold this block still and you push on this one, to break the static friction, you need a force of 12 newtons, right? At least 12 newtons. So that's like our maximum static frictional force. That's telling us that here the max static frictional force is 12 newtons. You go more than that, you break, then you're going to break the static friction. And I suppose while we're at it here, we might as well just figure out what that coefficient of static friction is. So I know that that's equal to static coefficient times the normal force. That's just sitting straight on top of that, so that means the static coefficient would be equal to 12 newtons divided by the normal force, which would just be 4g. So that's 12 newtons divided by 4. That's 9.8. It's about 0.3. I'm going to say 0.306. I feel kind of funny about rounding that to 0.31. So I'm going to keep that third decimal place there for now. Okay. Now the assembly of blocks is now placed on a horizontal frictionless table, and we want to know the magnitudes of the maximum force F that can be applied to the lower block so that the blocks will move together and the resulting acceleration of the blocks. All right, so now here the coefficient of friction between this block and the table here, they're both placed on a frictionless table. So I still have friction here. If there was no friction, maybe just think about this for a second. If there was no friction here either, then what would happen when you pulled on the 5 kilogram block? Well, you know the trick with a tablecloth, right? This would just stay still. This would just slide out from under it, and then that would drop or fall off. But there is friction there, so they can move together, but only up to a point, right? Because if we break 12 newtons of friction here, then it's going to, the top block will start to slide, right? So, and I think we're interested in that maximum, right? So the maximum horizontal force F. Well, in that maximum condition, that would be the condition where this has the maximum force on it. So let's think about this for a second. What is the direction of the frictional force? If there was no friction, this block would just slide off this way. So the friction must be this way. And in fact, you could also justify it by saying, well, that would be the only force that's moving this block forward, right? This force is not acting on this block. It's just the friction between these that's keeping it moving with this one, keeping it stuck to this. And we know that that maxes out at 12 newtons. Gravitational force would be 4g. Normal force here would also be 4g. So those are the forces acting on this block. Now here, on the bottom block, we have the force F. We don't know what that is. We would like to know. And we have a gravitational force, 5g. And we have the normal force. Actually, before I draw that arrow in there, let's just think about everything that's going on here. This block, the 5 kilogram block, has this block sitting on top of it, right? So this normal force here is an interaction between these two blocks. So if there's a 4g force up on this block, there must also be a 4G force down on this one. And you could call that a normal force, right? It's a perpendicular to that surface that's facing down there, right? And I think that that should make sense. Now the normal force here, to make that look a little longer, would have to balance both of those. It would have to be 9G. And again, this should make sense because if you put a bathroom scale underneath these, it's going to register the weight of both blocks. It's going to tell you that there's 9G. It's going to have to push up that hard, right? Because it's got this block, but there's also this block pushing down on it, right? So that's a very important thing to realize there when you've got blocks stacked up like that. And I think there's the intuitive sense that the normal force, which is like what the scale reading would of course be 9G, the sum, and then how you deal with that here, right? Also, there's another Newton's third law pair going on here, that if there's friction here between the two blocks, that's an interaction between these two blocks. So there must also be a frictional force of the same exact magnitude here, right? So this friction is coming, it's on the 4 kilogram block from the 5 kilogram block. Then there also must be the same amount of friction on the 5 kilogram block from the 4 kilogram block. It cannot be otherwise. That is a Newton's third law pair. If this body and this body interact, then the magnitudes of those interaction forces on each body are equal but opposite in direction. So this would be a place, I think, definitely to pause and sort of ponder this and see if you can take this problem home from there. I think drawing those diagrams, especially this one, is maybe the tricky part where things might possibly have gone wrong for you. So if you think you understand what's going on here now, or even if you don't, then pause the video here and get yourself to where you understand what's going on here, and then try the rest of it yourself. Okay, welcome back if you paused. So here I'm going to do the next step. Sum of all forces on this block, it's just that static frictional force. Sum of all forces on this block, we have the force F, that applied force, minus that static frictional force. And just like a tension, those interaction forces cancel each other out in those two equations if we add them together. That's what we're going to do. So this is 4A, this is 5A. Add those together, and 9A is equal to F, right? And, and I also know, and I think I forgot to put in here, I know what this is, don't I? That's 12 newtons. So this force of static friction here, so I think I can find right here, plugging that in, that 4A is equal to 12 newtons. So A would be equal to 3 meters per second squared. So that means the force is 9 times that, be 27 newtons. And the resulting, so I think I found the two parts, right? They both came out of that system of equations. And so my computer went to sleep here, so before I lead you any further, just make sure that that's right, and those are the right answers. Cool. That's a good problem. That's number 61. Okay, that was a long problem, 9 minutes. All right, let's see if we can pick up the pace a little bit here. So 79, what we got here? We have more blocks, and let's see what we have. Looks kind of like this. Here's my pulley. Here's block A and block B. And it looks like I've got friction here. And let's see, mass A, that's this one, is 4 kilograms. And this one is 2 kilograms. And let's see, this no more information on that page. And this kinetic coefficient is 0.50. The inclined plane here is frictionless. And the angle here is 30 degrees. This seems familiar. I've done something like this recently. The pulley serves only to change the direction of the cord connecting the blocks. So in other words, it's frictionless and massless. And we want to find the tension of the cord and the magnitude of the acceleration of the blocks. All right. So let's see, force diagrams. This should be pretty familiar now. So I have this force of gravity. You should be ready to pause at any moment if you think you realize something that you didn't before. So there's the components of the gravitational force, and the normal force would be balancing out that part of gravity, right, like it always does. And no friction here, but we do have tension. Well, I'm going to make that small because I know that when I release these, that this part of gravity is going to be winning. They're going to slide down the ramp. Okay? And then on this block, I have a gravitational force of 2g, a normal force, sorry, it's squiggle there, of 2g, balancing that, and I have a frictional force opposing the direction of motion. It's kinetic friction. And I have a tension force that's winning because the blocks are going to go that way. All right, sum of all forces on this block would be 4g sine 30, winning, minus tension, losing. This block, sum of all forces, tension winning, and kinetic friction losing. I need a little bit more room up here, so I'm just going to continue. You can keep moving straight down. So mass times acceleration is equal to, the sine of 30 is 1/2, so that's 2g minus t. For this block, I have 2a, it's mass times acceleration, is equal to t minus the force of kinetic friction is the coefficient times the normal force. So that'd be 0.50 times 2g, or in other words, just g. Or as my friend Patrick Orseau says, he's from France, he would say G. And so we add these equations together, and we get that the acceleration is 1/6 g. And is that what they want? Tension in the cord and the magnitude of the acceleration. So that's the magnitude of the acceleration. By the way, that's approximately free fall acceleration on the moon. It's about 1/6 what it is here. So 9.8 divided by 6, about 1. Whoops. And so the decimal place is off there, about 1.6. Lost my decimal. And part A, they wanted the tension. So one of these, you could say it's about 1.6 times 2, and then add the plus g. So it'd be about 13 newtons. And I'm pretty confident about that, but we better just check to make sure. 13 newtons and 1.6 meters per second squared. That's correct. Cool. All right, let's do that. Let's just use a new piece. No, let's use the back of this. 87 next. Okay, so we have now a car weighing 10.7 kilonewtons, and weight is the same as gravitational force, right? Make no mistake about that. It's traveling at 13.4 meters per second. The book says without negative lift. You can engineer cars so that they have negative lift, which means that, if you put spoilers and things on them, you make them a certain shape, it actually helps the car push down a little bit, which increases the normal force, increases friction, makes it a little bit safer. So anyway, we're ignoring that. We're not dealing with that kind of craziness. So when it says without negative lift, it just means that you don't have to worry about anything. It just means that the up and down forces will in fact just be this. The normal force will just match this. He goes around a turn of radius 61 meters. What's the magnitude of the frictional force on the tires required to keep the car on its circular path? Well, we've seen this problem before, something very similar. So the gravitational force is the 10.7 kilonewtons. If that's freaking you out, you can write that. Normal force would match that, right? Because there's no other forces in that direction, no negative lift or any funny business. And if we're looking at the tail lights and it's making a left turn, then the force of static friction between the tires and the road would have to be that away, right, toward the center of the circle. Okay, so this is the only thing providing the centripetal force necessary to move it in the circle. So static friction, the coefficient of static friction times the normal force be equal to mv squared over r. That's the relationship that would have to hold true. And that's the equation that would give the maximum velocity. But they want to know what's the magnitude of the frictional force that's required to keep the car on its circular path. Well, that would be this side of the equation, right? How much frictional force would there have to be? That'd have to be mv squared over r. So let me figure that out. There would be m, which would be 10,700 over 9.8, that's the mass of that, times the velocity squared over the radius of the turn, which is 61. Oops, sorry, put the wrong number there. Sorry, that's mv squared over r. There we go. Let me get that in the calculator, see what it says, and we'll see if we got enough friction to make this turn. 10,700 divided by 9.8 times 13.4 squared all over 61. I don't need parentheses there because it's divided just by one number. So we would need about 3,200 newtons, give or take. And we need to know here from this side of the equation, my maximum amount of static friction. They told me, what if the coefficient is 0.35? Then the maximum would be that times the normal force, 1,700 newtons. So it looks like it's going to be close. 10,700 newtons times 0.35. Uh-oh. About 3,750 newtons or so. So that's how much would, oh, wait a minute. No, we're good, right? Because this is the maximum amount of static friction. We can provide this much maximum, and this is how much we need to make the turn, right? This is the centripetal force required to make the turn. This is how much we can get from static friction, max. So we're good. We made it. Let's see what the book says. The book would agree with those answers. They gave this as, they kept 3 sig figs. They gave that as 3,210, but hey. All right, what's next? 91. This is fun doing all these homework problems with you guys. I love physics. So 91, a block slides with a constant velocity down an inclined plane that is sloped at an angle theta. Now if it's going at a constant velocity, then what does that mean? It means the forces are balanced. So we'd have here, this would be mg cosine theta, this would be mg sine theta. The normal force would be balancing this part of the gravitational force like it does in every single problem, be equal to mg cosine theta. And then if it's moving at a constant velocity, then the frictional force, the kinetic frictional force, would be equal to that. Right? So I think we can find the kinetic coefficient, right? If we wanted to. Couldn't we? Could we not? I think we could. I don't know if we actually need to do that to do this problem. I have a feeling that we don't. But I'm going to do it anyway. So here I know that mg sine theta is equal to the force of kinetic friction, which is equal to mu k times the normal force, g cosine theta. And this is, one of the reasons why I wanted to do this anyway, is just so you could see what happens here in this particular problem. It's kind of interesting. It turns out the coefficient of kinetic friction in this situation where the forces are balanced and it's sliding at a constant velocity down the ramp, that the coefficient of friction is just equal to the tangent angle of the angle. Kind of cool, don't you think? So that's interesting to see, but I don't think we need it to do that to answer the question. They want to know how far up the plane will it come before going to rest if it initially, instead of just sliding down the ramp at a constant velocity, if it's given an initial velocity of v sub 0. Well, that sounds kind of like kinematics, doesn't it? I think that we would first have to realize that in that situation, the force diagram's a little bit different, because if it's going up the ramp with an initial velocity, I put that in a bad place, didn't I? The normal force is going to go crashing right through that. The normal force, mg cosine theta, that's still the same. But now, these are all the same, mg cosine theta, mg sine theta, like they are in every single problem. Now that it's going up the ramp, friction always opposes the direction of motion. So here, the kinetic frictional force is going to be down the ramp. So the sum of all forces on this block, it's these two are both fighting against the velocity. So we're going to have to make a call here about signs and directions in a minute. I'm just going to say this is the direction of winning, so it's the kinetic frictional force plus that part of gravity, because they're both down the ramp now. If it's going that way, friction's going the other way. So let's see what we can do with this. So mass times acceleration is equal to the force of kinetic friction is equal to the coefficient of kinetic friction times mg cosine theta plus mg sine theta. Maybe we did need that after all. Who knows? So those all cancel out. And so the acceleration of the block is equal to the coefficient of kinetic friction, which is tangent theta, times g times cosine of theta plus, oh, you know what, there's an easier way. And then this is sine over cosine, so the cosines cancel out. Yeah, that's 2g sine theta. But you know what, there was an easier way to do that, because we knew from before that these two things are equal to each other, right? The amount of kinetic friction is the same, right? None of these things have changed. So if it's the same, of course, this is mg sine theta, and so is this. So it's two of those. But either way, you get to the same place. Okay, so now we have a kinematics problem. And I'm going to say that up the ramp, that this is the positive direction. Okay? So, what do I know? Or what do I want to know? I want to know how far up the ramp is it going to go. So that would be, I'm going to call it delta x. The delta x is what I'm looking for. If this is the positive direction, then the initial velocity is v sub 0. Right? They told us that. If I want to know how far up the ramp does it go, that means going until it has a final velocity of 0. Right? That's where it would stop momentarily, or maybe for good. We'll deal with that in a minute. And the acceleration, I know, is 2g sine theta. But the acceleration is down the ramp, right, in that direction. So that's a negative acceleration. So delta x with these, oh boy, you remember these equations? Sometimes they just come up, and you're supposed to know them. That's crazy. So let's see. This is 0, so I get 0 is equal to v sub 0 squared plus 2a, I guess that would be, I could write that as minus 4g sine theta, is delta x. So delta x looks like it would be v sub 0 squared over 4g sine theta. I don't know what you think, but I think that's just a beautiful result. Oops, sorry, it'd be nice if you could see it, huh? There it is. So not knowing any of the actual numbers, we can come up with that determination. I think that's a nice result. And for part B, after the block comes to rest, will it slide down the plane again? Well, I suppose it could, but it's very likely, I think, that it wouldn't, because what we've seen is that coefficients of static friction are almost always bigger than coefficients of kinetic friction. So when it gets to the very top and stops just for an instant, static friction is going to take over if it can. And since the ramp is set at that angle where the forces are balanced, if the static coefficient is even the tiniest bit bigger than this, then it's going to stick, right? Because the forces were balanced here when it was sliding down the ramp. So answer for B, will it slide down the plane again? The answer would be no, and the justification would be all the coefficients of static friction that we've seen, that they're almost always bigger. So if it's bigger, then the answer would be no. A joyous problem that was. And then 96, last one. This is a little easier here. So another circular motion problem here, not to forget about that. A child places a picnic basket on the outer rim of a merry-go-round that has a radius of 4.6 meters and revolves once every 30 seconds. So it goes around once. So let's say this. Let's say 1 revolution per 30 seconds. What's the speed of a point on that rim? So if we've got a circle here with a radius of 4.6, there might be an equation that you remember, but you might also just say, well, I guess this is the equation one way or another. The speed of something at this point on the circle, the speed of anything moving in a circle. Speed is just distance over time, so 2 pi r, that's the distance around the whole circle, over the amount of time it takes to go around the whole circle, and that's 30 seconds, so it'd be 2 pi r, r is 4.6 meters over 30 seconds, so that's about 2 pi times 4.6 over 30, about 0.96 meters per second, right? And I think that's the answer for part A, isn't it? And part B, what's the lowest value of the coefficient of static friction between the basket and the merry-go-round that allows the basket to stay on the ride? All right, well, the forces, draw the same kind of force diagram we've drawn before. Don't know the mass of it. Gravitational force would be mg then, and so would the normal force. and then there must be some static frictional force. Doing the same kind of diagram where I'm imagining that the basket's going into the page and going around the circle like this. So that means the unbalanced force toward the center of the circle is coming from static friction. So the static frictional coefficient times the normal force would be equal to mv squared over r. M's cancel out. And so we're going to find the smallest possible number this could be. If it was bigger, maybe it would have more static friction than we needed, right? If that, we wouldn't be maxing it out. But we're doing the maxed out condition here. So that's what we're trying to solve for. So that's just going to be v squared over gr. And we know the velocity. We found it in part A. Over 9.8 times Well, let's see what that is. 0.96 squared divided by 9.8 times, oops, almost made that rookie mistake. 4.6. 0.020. Now let's reflect on that for a second. You might be looking at that number and thinking, that's awfully low for a static coefficient. But this merry-go-round is not going very fast. And the question was, what would the minimum coefficient of static friction need to be? So we could come away from this problem saying, under these conditions, this picnic basket is quite safe, right? We could assume that it probably has a static coefficient of at least 0.4, 0.5, something like that. So it's not even close to going, the merry-go-round is not spinning so fast that this thing would require so much centripetal force that we start to get to the edge where it's going to slip off. It's not even coming close to slipping, right? This means that we would only have to have a coefficient of static friction of 0.020 for it to be at the very edge, like slipping. So there you go. So this does not mean that that's what the coefficient of friction is. It means that this is the minimum value so that it doesn't slip. Right? All right.